What we're covering in Chapter 13 is magnetic flux, which, much like electric flux, magnetic flux is the integral over a surface of the magnetic field dotted with a normal to the surface, right? So we get this B dot n hat dA. And, and we'll get to magnetic flux over a closed surface later. That's an easy one. It's always zero. So Faraday's law Faraday looked at magnetic flux, and what he discovered is that if you have a loop of wire, or let's say you have multiple loops of wire, so a coil of some sort, and that has n turns going around, n windings, that the electromotive force, the EMF induced in the coil, right? This is like a voltage, it's electrical potential. It goes as minus the number of turns, minus n, times the derivative of the magnetic flux with respect to time. What does that mean? So let's look at just one coil, right? And we're going to consider the magnetic flux coming up and out of that coil. And I've drawn this little arrow here because as the flux increases, right? As the flux increases, what happens is you actually get an EMF induced in the opposite direction to the right-hand rule. That's why this little negative sign is there. Why? What the EMF is doing, if you look at what that EMF does, that EMF produces a magnetic field that goes the other way. Right? So if you have a current circling around this way, you're producing a magnetic field that opposes the increase in the magnetic field there. That's what this little negative sign is kind of trying to tell us here. And this is a basic principle in nature. The EMF induced opposes the changing magnetic flux by creating a magnetic flux heading in the opposite direction. Nature just doesn't like change in some instances, and this is one. And so it's the negative of derivative, right? Likewise, in the same scenario, all right? In the same scenario, magnetic field's coming up out of here, but if the magnetic field is dropping, so the flux is dropping, this minus sign ends up canceling the minus sign from the decrease in flux and becomes positive. And what happens is you induce a flux, a magnetic field, you induce an EMF going counterclockwise that produces a magnetic field that's trying to keep the flux up where it was. So if the flux is increasing, you get a magnetic field that opposes it. If the flux is decreasing, you get a magnetic field that supports it. In both instances, you're opposing change because of that little minus sign right there. Another instance of EMF that we could actually measure around the NMR is if we've got a magnetic field, and let's say this magnetic field is coming up out of the page here. Let's pretend those little circles with dots in the middle indicating it's coming up out of the page. And I've got some piece of metal or bar that I'm moving in this direction, then that induces an electromotive force along the length of that bar. Electromotive force is proportional to the magnetic field, the length of the bar in the magnetic field, and the velocity v with which it's moving. Right? And so you can actually measure this by waving a screwdriver around near the NMR and measuring the pinch along the length of the screwdriver. And you can feel the magnetic field if you're waving a screwdriver along. And note, this doesn't have to be a magnetic material of any sort. This can be any conductor, right? So any conductor that you wave through a magnetic field induces an EMF, proportional to the magnetic field, the length of it, and the velocity with which you're moving it, right? So the faster you move it, the more EMF you get. If you think about motional EMF in a circuit, we can now take a closed ring, right? If this is a closed ring, like a wedding band or something like that, or just a loop of wire that's connected all the way around, and you got a changing magnetic flux through that induces an EMF around it, and you actually get current flow around the ring. So you get current going around in a circle around the ring. So again, you get an electric field, and this is just integrating electric field along the wire, and you get E dot dl summing up to the electromotive force on voltage in the loop around the wire. So unlike a standard circuit where we're using some source to produce this, if you start here and you go all the way around and you come back to the same spot, you've not come back to the same potential. You've actually gone through a net increase in potential. It is uphill both ways all the way, all right? And so this is a little different from standard circuits and what goes on there. And the final little bit for this set of homeworks, we have EMF produced by an electric generator, which a generator, electric motor or something like that, you basically have coils of wire moving in a big magnetic, between two big magnets, right? So you got coils of wire, you're rotating them, and as you rotate them, they go back and forth through the magnetic field generated by the magnets. And what we have here, that's the number of windings on the motor. B is the magnetic field. A is the area covered by the coils, and omega is the rotational velocity, where omega is 2 pi times the frequency, 2 pi f. All right, omega is 2 pi f. And that's it for chapter 13, and hopefully this will help get you into the problems. And each of them problem there should be an explanation for the ones you missed. So that's it for chapter 13.